that a state space representation can handle the
Handle what?
the integrals, because we still don't have a closed form.
Right.
So it would just have to discretely calculate it over the length of the length.
Right. So you don't get a full. But my guess is that this L, these guys here.
Yeah.
The L perpendicular, D perpendicular, the L parallel, D parallel.
Yeah.
Right. These are functions of. This is just this integral here, right?
Right.
But there's only a couple of terms of it are functions of radius, right?
Uh-huh.
In other words, you're saying, oh, we can't do a closed form solution. Is that dt or dr?
dr.
Okay. So v is a function of r.
Right.
And alpha is a function of r.
Right.
Right. And you're saying we can't. Have you actually plotted what those are?
Yeah.
Your v and your alpha is a function of r.
Yeah.
Okay.
Yeah.
And you're saying you can't find a closed form solution for it.
No.
Okay. Well, to a certain extent, what you can do to make it easy is you can make a lookup table, right? You just basically do the integral in a whole bunch of different places, and then you map it and you say, hey, can I fit a line to this? On any given thing, and not just pull it out.
So some sort of approximation.
Yeah, just interpolate it between points.
Okay.
Would be the way to do it. The thing is, this is a function of. So right now, this is L perpendicular as a function of z dot.
Right.
You want to get that to an L some coefficient times the v dot, right? You want to get to this point. Right?
Just like a regular.
Yeah.
Well,
it doesn't matter. You want some approximation for it.
Yeah.
Right. If you want if it comes up to a linear approximation, which is coefficient times z dot, then integral. Right. At that point, drops into the state space dot v dot. If it's not, the same thing with d. Right. If it's not a linear approximation, you can't come up with a close linear approximation, then you're kind of screwed. But then what we're going to do is we're going to do a perturbation. Right. Because you say, look, I'm going to control it about some nominal point, right? And I'm going to wind up with taking it about some nominal thing where I've got at some nominal point, I've got at some vertical velocity, right? And then what I want to do is I want to say, hey, what is my delta z dot, right? So you're going to get that z dot is equal to my nominal velocity plus some small perturbation.
Right.
And then you can go through all of this. I don't care how nonlinear it is. You go through, insert it all through, throw away higher order terms, and you say, I'm close to this one.
Yeah.
Subtract out the nominal thing, and the thing will drop down to linear control.
Okay.
And you wind up, then you just have to keep changing. It'll be as a function of z dot 0, right? Which means your nominal control system will be built around whatever nominal your ascent or descent rate is.
Okay.
And then you can do that. And that will always work. That perturbation will always work. It will always give you a nominal function. Right. Right. Because essentially what you're doing is a first order Taylor series.
Okay. Gotcha.
So, for instance, let's say I have, as an example of one that I did, I have something. This is an angle. It's called phi, right? And I generate a lift in that direction and a drag in this direction, even though my nominal speed is in this direction.
Right.
Right. So in this case, I create a parallel, perpendicular, or actually, I just create a force like this.
Yeah.
There's my normal force, and then my lift. Right. So my lift is approximately to n cosine v.
Right.
And my drag here is equal to n sine v. Okay. And you say that my lift here, my total n, my n is equal to some coefficient of lift times v naught based on some speed times this sine theta. Okay, so that's n. So now you say, okay, so lift is equal to now CL V naught sine theta cosine theta. Not linear, right?
Right.
Massively so, right? And you say, all right, well, if I'm trying to control, let's just say this is the only one in the vertical direction. I'm trying to control vertical direction, right? I've got mg that's pulling down.
Yeah.
I've got here's my coordinate system if I'm looking at y. So I've got my double dot is equal to mg minus mg, so it's going to be CL v naught sine theta cosine theta minus mg. And you say, okay, right, now I want to control my altitude, I control y
Yeah.
with theta. So I say, okay, screwed. It's not linear. Right? How am I going to do this? Well, the answer is, I say, okay, fine. Like, theta is defined as some theta naught plus a delta theta. Right? Small. Sure. Okay. Higher order terms. So now I'm going to say, nominally, if this thing is all said and done, right, nothing is moving, I'm in steady state. Steady state means I'm not declining or ascending, which means that term is zero. Okay? Which says that 0 equals CL V naught sine theta naught cosine theta naught minus mg. Right? And I can say, oh, well, I can tell you that sine cosine theta turns out to be sine squared 2 theta over, I believe, the whole thing over 2. There's some trig function. You can find it.
Yeah.
I think that's it, but I'm not. I did it long enough ago that I remember. But you say, oh, well, that equals to mg over CL V naught, right? And you're like, oh, I can actually tell you what theta naught has to equal based on this stuff in order for the thing to be. Then I go through, here's the key, right? Remember, this is 0, right?
Yeah.
Now I'm going to say m, and I'm going to have y plus delta y naught plus delta y, double dot. That's a constant, so that goes away.
Yeah.
So it really becomes m delta y double dot. This is a nominal deviation off of my current altitude.
Yeah.
Right? Is going to equal to, and then I'm going to have this CL V naught, and I'm going to have sine of theta naught plus delta theta,
Right.
times cosine of theta naught plus delta theta. I'm going to do a double angle expansion on all of these. I'm going to start doing them. I'm going to say that sine of delta theta is approximately delta theta. Cosine of delta theta is approximately 1.
Okay.
Right? The other ones stay. Right? Expand everything out, minus mg. You will find this term will show up and subtract off because that's equal to 0.
Sure.
Right? And so what you'll be left with is you'll get an mdy double dot is going to equal to something with linear terms of theta naught. There's going to be some funky coefficient in front of there.
Okay.
There's going to be it's going to be a CL V naught times a cosine theta naught or something like that. It'll be there. You know what theta naught is from this one, right down here.
Yeah.
So it's coefficient. But it doesn't matter. At that point, you're back to a linear equation. I can wrap a control system around that. And I'm done. Right? And that's always going to work. It will work with that thing. Okay. Right? Whether you can do the integrals or not, whether you can find a closed form, it doesn't matter. You can just expand it. Higher order terms drop out.
Right.
And then you can go.
Okay.
Right. So and at whatever nominal z dot you have, doesn't matter if I can solve them analytically. I can solve them numerically. Right. So I can solve them numerically. I can then have the differential part sort of do that, come up with an approximation for it, and move on. So that's what we do. All right, you okay?
Yeah, I'm fine.
All right. All right. Where did I put my box of spark fun stuff? Oh, no. All right. All right.
All right. Thanks for coming by.
You're welcome.
When is your office hours?
Right now they're still being established. I won't be here next week until Friday.
Got
So you can just come by Friday next week. We'll do the same.
it. Sure.
All right. And then we'll move on. But meanwhile, just so you know, Pat Mack is actually quite impressed.
Oh.
He's like, boy, this guy's working hard. I was like, yeah.
We're putting in a lot of hours.
Yeah.
Yeah.
I'm not sure what you're doing, Paul, but you're putting in a lot of hours.
We're going slow. We're taking our time.
Good. And you're having fun.
Yeah.
Yeah.
Definitely.
I still think that at this scale you're not actually gonna be able to fly. But
No.
I don't think you can generate enough lift, or barely generate enough lift to fly. Although apparently you flew, so
Little.
a little, which is fine.
We-
Great
yeah.
for testing,
Right.
right? Because all that happens is you scale this thing up to a meter, and all of a sudden it will fly.
Yeah. Yeah. That's.
And it should be fun, by the way, once you sort of get it up and you have it sort of throttle speed.
Yeah.
Your coefficients are going to be off, right? For all of your various coefficients for everything that you set up the equations to predict everything.
Yeah.
But you should be able to take a couple of experiments with what you've got
Mm.
and say, hey, I can actually model
Yeah.
these coefficients,
Bring it back.
and I can actually take some experimental data and say, what do the coefficients have to be to match this experimental data? Now I've got a better model of my actual system.
Okay. And then come back to this.
Exactly.
All right.
So keep it symbolic. You guys
Okay.
are probably going to have to teach you guys MATLAB at some point. I like your little
Fun
fun
cutter.
cutter.
Yeah.
You guys did.
Andrew's very proud of that.
Yes, did it actually work?
Yeah.
Very well.
Phenomenally. All of these are full of you cut with that.
Oh yeah?
Yeah.
Cute. And what the hell is this little thing?
Also bought from Mike.
Yeah.
Yeah.
Well, it's got a little extra motors. Look a little suspiciously like similar motors, actually.
I think they're a lot smaller.
Yeah.
These are bigger.
Those are bigger?
Yeah.
All right, cool. Good.
Yeah.
All right. So yeah, you have some issues